Thank you. Yes, my talk is about topological defects in Landau-Ginzburg models, and I shall concentrate on two of the properties. The first property is that defects can act on bulk fields, and I will show that this can be rigorously described if one endows a certain category of matrix factorizations with a rigid monoidal structure, which will be compatible with its triangulated structure. The second property is that defects can also act on themselves or on each other and on boundary conditions, which is a process called defect fusion. And I will explain how, if one has this under good control, defect fusion allows us to explicitly compute categorified link invariants like the ones proposed by Khovanov and Rozansky. To define what a two-dimensional topological field theory with defects is, we can follow the usual approach and define a certain symmetric monoidal functor where the source category will not only have labels for boundaries but also for defects. But unfortunately, so far opposed to the case of only open and closed sectors, we do not have a complete algebraic description in terms of Frobenius algebras and Calabi-Yau categories. So instead of explaining this in detail, I will use only certain properties of topological theories with defects. In particular, every correlator that we associate to a worldsheet that is decorated with defect lines, and on them and or at the junctions we can insert additional degrees of freedom, defect fields. By definition, these correlators will have the property that their values do not change if we vary the position of the defect lines, as long as they do not cross field insertions. So that's the defining property. And in the different faces of the worldsheet, for example, this face or this face, into which the worldsheet is partitioned by the defect lines, we may have different theories. So in particular, if all the faces are described by Landau-Ginzburg models.
Excuse me. So this linear is drawing the Riemann surface?
Yes. Yeah. This is a part of the Riemann surface. That's why it's dashed here. It can also have boundaries. But I forget the conformal structure. I only look at topological field theories. In the case where we have Landau-Ginzburg models, defects between a theory with potential W1 and W2 will be described by matrix factorizations of their difference, and the degrees of freedom will be the morphisms in this triangulated category. Well, we always have one particular defect, which is the invisible defect. That's the one that I didn't draw here, for example. And it has the property, by definition, that it can move through even field insertions. So in particular, if one can imagine that every bulk field, like the one 5,3 over here, to be sitting on top of the invisible defect. So we would expect that the defect changing operators that sit on the invisible defect are the same as the bulk algebra, and that's indeed the case. So one knows that the invisible defect is described by this simple causal type of matrix factorization, and its endomorphism algebra is precisely the Jacobian, which is the bulk sector. Now, a property of defects that goes beyond that of boundary conditions, which are also described by matrix factorization of just one potential, is that we can fuse them together if they're topological. So if the position of two defects does not make a difference, we can put them on top of each other, and we get a new defect line, which I suggestively denote by the tensor product of the two here, which will then be a defect between theory 1 and theory 3, and theory 2 in between will be squeezed out. It's a tensor product because one can show that the category of matrix factorizations of the difference where we have the same theory on both sides is a monoidal category, which means that and the tensor product is the one that you would expect, the graded tensor product. And you have associativity for this fusion, and you have coherent morphisms which act with the invisible defect on every defect from both the left and from the right. So we can give the explicit isomorphisms and their inverses, and this allows us to do explicit computations, like, for example, that of 6J symbols, which in conformal field theory are also called fusing matrices. And then there's the duality, often referred to as the CFT Landau-Ginzburg correspondence, and we find agreement in these two approaches. One should also mention that this monoidal structure on the category of endo defects, that is where both sides of the defects are described by the same theory, are really just part of a bigger structure of a bicategory, where the objects are theories described by potentials W. The one morphisms are the defects in between, so matrix factorizations, and the two morphisms are the defect fields. This is a structure that is studied in detail by Lazaroyo, mostly in unpublished work. But before I talk more about the fusion of defects, I'd like to tell you about the action of defects on bulk fields. So what we can do is we look at the particular part of the worldsheet and a part where we have an insertion of a bulk field phi, and then we wrap around this field a defect line labeled by x. But because this is a topological defect by assumption, we can ask what happens if we collapse that defect onto the bulk field. So there will be no defect line left because everything will be at that point. So we get a new defect field, which I might call phi x. Though I always used to be a little baffled by what exactly this means. Well, one can talk about this rigorously if one has a rigid monoidal structure in the category of defects. So this picture that I drew over there can be rigorously interpreted as this. As I said before, any bulk field phi can be viewed as an endomorphism of the identity defect or invisible defect. And then the action, say the right action, so if we wrap around in this fashion, clockwise, of a defect x is defined by this diagram. So we have 1, 2, 3, 4, 5 maps here, 2 of which are the right action of the invisible defect on the defect x and its inverse, and then phi itself. And these 2 here are precisely evaluation and co-evaluation maps, which take the inverse or dual of the defect, where we have inverse the orientation, reverse the orientation, tensor or fused with the defect itself, and we map to the identity defect and also the other way around. And you would expect that such maps satisfy these relations over here, because we can always straighten out such an S to make it completely straight. But the existence of such maps for every object x that satisfy these duality rules here is precisely what it means that we have a rigid monoidal structure on the category of defects. And we prove that this is indeed the case. It's also pivotal, which means that there's a nice relation between taking the double dual and the identity functor, so not doing anything at all. It's a monoidal natural transformation between the two. Actually, Ingo Runke and I only did this properly for n equals 1. We have very explicit formulas there. But ever since we wrote this paper, then Murphy and I have been working on this, and we are nearly done with extending it very explicitly and actually nicer to the arbitrary case, where we have arbitrarily many fields in our Landau-Ginzburg models. N was the number of variables of chiral fields in the Landau-Ginzburg model. Right. Another result is that this right action of defects, where we wrap around clockwise, we also have the other one where we wrap around counterclockwise, which we call the L. These really induce ring homomorphisms or anti-homomorphisms from the complexified Grothendieck group, which is actually a Grothendieck ring together with fusion of the category of matrix factorizations, into the degree-preserving operators on the endomorphism algebra of the identity defect, which is nothing but the bulk fields. So this means, because the triangulated structure goes into the definition of the Grothendieck group, we find that we have this compatibility between the rigid structure and the triangulated structure, as you would expect, which is also the case in rational conformal field theory. Another way to arrive at a formula for the action of bulk fields is to use what is called the folding trick, which allows us to express this bulk correlator with the presence of a defect action on phi in terms of a boundary correlator, again with a bulk field phi and psi, but inserted on a disk that is bounded by a boundary condition that comes from the defect condition x in the folded theory. And this suggests that this residue or Kapustin-Lie kind of formula is the formula for the action of the defect x on the bulk field phi, and we check that this is really true. So this also follows from our approach from using the rigid structure, that is the evaluation and co-evaluation maps, with the picture that I showed you earlier. Another result is that you might expect that the left action and the right action, that is wrapping around a defect in one direction or the other direction, are joined with respect to each other. And this is actually true for all the defects that we know in the case where the Landau-Ginzburg model depends on only one chiral field. And it is expected to be true also in the general case, because pictorially what you do is you wrap around the defect in one direction around phi, and then on the Riemann sphere, because everything is on tree level, you can wrap this around the whole sphere, and then you have a loop around psi, but in the other direction. So this picture is exactly the same as this formula, so we think this should hold generally. Now let me go from the action of bulk fields to another action of defects, but on themselves. And this will allow us to compute explicitly Khovanov Rozansky link homology. So before I tell you how to do this, I would like to recall a little bit how they categorified certain link invariants. They would start with any link embedded into three-dimensional space. So for example, we can look at this projection on a plane here where we have overcrossings and undercrossings. And then to each crossing, we can associate a certain kind of resolution. So take, for example, this crossing here and replace it either, all my links are oriented for the rest of my talk. So there should really be arrows here. So take this, say this crossing, replace it either by this or by this. And in this way, we get an oriented planar graph that has only 4 valent vertices, namely precisely these. And then, given such a graph, we do this for all the crossings. We number all the edges in that graph, and to the nth edge, we associate the variable xn. Furthermore, to a crossing of this type, a resolution of such a crossing, we associate a certain matrix factorization that I call x circle, and to such a crossing here, which really is a vertex in the graph, we associate another matrix factorization, x bullet, which will be matrix factorizations of this particular potential, where these two x's really depend on the ijkl labels over here. So one way you can interpret this is that x bullet and x circle are defects between this theory and this theory. And later, right now, I will tell you that you have to fuse them. So Khovanov and Rozansky tell us, once we have built up such a graph, we take all these different vertices, take the tensor product over them, and in this way we get a matrix factorization of 0, because you will see tensoring adds potentials, but there's no, it's not a tangle, not a non-trivial tangle, so there will be no ingoing and outgoing edges. So in the end, we will get a matrix factorization of 0, that is w minus w, if we add over all the vertices. But the matrix factorization of 0 is the same as a complex. And it will be this complex over the ground field, which is taken to be the rational numbers, that we will compute. But the way we compute this is we really want to start with a whole link diagram, and then to each crossing, if it's an overcrossing, say, let's say this is an overcrossing, we associate to that overcrossing really a complex of matrix factorizations that have an additional R charge shift. And all the other entries in that complex will be 0. So here's a map to 0, here's a map from 0, and there's a non-trivial map chi naught. So I will not give you the explicit expressions for maps like this and these matrix factorizations over here, but Khovanov and Rozansky provide them. And to an undercrossing, that is that kind of crossing, we associate again a little complex of matrix factorizations, where now here this is the homological degree 0, and another map chi 1. Now, in order to get from this data the categorified link invariants that Khovanov and Rozansky described, is we tensor over all the possible crossings all these little complexes. So to each crossing I associated a complex of matrix factorizations, and now we tensor over all these crossings, and because matrix factorizations are z times z2 graded, R charge and the usual z2 grading, and because we have the homological degree that comes from all these complexes, we have another z factor. So we have that kind of complex over Q, and by definition, Khovanov Rozansky homology is the homology of this complex. Now they prove that the homology of this complex is an invariant, so independent of which projection of the link that you choose, you get the same thing up to isomorphism. So all the, this is invariant under Reidemeister moves in one word. And it's also concentrated in exactly one Z2 degree, depends on the number of components of the link. And then if you take the Poincaré polynomial of the of this homology, then this is one way to encode this theory, and it's a categorification of the better known and older SLN link invariance, which you get if you set one of the variables equal to -1. But this is a finer resolution. Good. But if we really want to compute this, we have to compute all the fusions of these matrix factorizations X bullet and X circle. But the problem is that if you fuse to matrix factorizations, then the resulting matrix factorization will still depend on the variables of the theory in between. So this is no good if you really want to compute a homology theory over Q, over the complex numbers. So more precisely, let's take a matrix factorization that depends on X and Y of W1 minus W2, and another one that depends on Y and Z, W2 minus W3. Then the tensor product is a matrix factorization of W1 minus W3, but it will still depend on Y. But it's a result, which is not that difficult to prove, that actually it is isomorphic to a finite rank matrix factorization T for tensor product that does not depend on Y. But nobody knows how to algorithmically compute that. Well, nobody but Tobias Bükerhoff and Dan Murphy in a sense, because what they give, they don't really give T itself, but they produce an idempotent on X tensor Y. And if you succeed in splitting that idempotent, you get exactly the finite rank matrix factorization T. It does not depend on the unwanted squeezed out variables. Now, there exist algorithms to compute the splitting of an idempotent, and we implemented such algorithms into the package Singular, Dan Murphy and I. And in this way, we can now give explicit formulas for arbitrary fusions of defects. In particular, we can fuse the matrix factorizations that occur in the construction of Khovanov and Rozansky, and therefore I will now be able to present you some results of these computations. So Khovanov and Rozansky have something that is called both reduced and unreduced SLN link invariance, and they also have a construction for SO2N. And in the rest of the talk, I will present some results for these links and knots in the case of SLN. And for us, it doesn't make a difference. We can compute both reduced and unreduced, whatever that is. I won't explain that. Though so far in the literature, there have not been any direct computations using Khovanov and Rozansky's construction, but only other approaches to the same thing. And they mostly concentrated on the reduced case. And we can compute examples that nobody has computed before, though there are also examples that are just too difficult for us to compute because it takes a lot of computing power. I'll show you that in a minute. So for example, for torus knots, the threshold or the sunk fall, we can compute some link invariance like this, or the figure 8 knot, we get this. Here's a knot that doesn't have a nice name, but we can also compute its Khovanov-Rozansky invariant. Here's a knot that has 8 crossings and is very well respected in the knot theory community because it's rather difficult because it's not a two-bridge knot. So one doesn't know how to compute this also using other methods. Well, and we can compute the n equals 2 case. That's not very good, but it turns out that if you really try to do this, so I show you what a screenshot looks like when you compute with our code a link invariant for the hop link. Well, it's very easy. So this is nice. There's very small numbers here, and it goes through very quickly in a matter of seconds. But if you compute more interesting knots, then with all the idempotent splitting and the reduction that are part of the code, you get really big numbers. So this is one number. These are 3 numbers, and this is 1 number. So it really takes a very long time. With the help of Nick Baer, we tried to put this knot on a supercomputer that has memory of at least 40 gigabytes, but it died. So we cannot compute everything. But we can also compute some links, actual links. Here, for example, is the hop link, or the whitehead link, or this link, which again doesn't have a nice name, I think. We can also compute links that have 3 components, like the Borromean rings here. There's actually 3 versions of them, and each individual version really comes in 4 versions, because depending on which orientation we choose for the individual links, we get different results. Well, actually, for most of the links that we have studied, this is not the case. But here, one of the 4 versions gives us a different result for the n equals 3 case than all the other ones. So that's one of the observations that we made. And we also can compute that for n equals 4. Thank you.
Actually, if you have this refined knot invariance, what kind of knots can you actually distinguish? I mean, where is it so to say good for the point of view of the knots here?
Well, I remember that when Khovanov introduced his Khovanov homology, which is the special case of Khovanov Rozansky for n equals 2, people found that this distinguishes knots that were not distinguished previously.
But what is the simplest knot?
But for Khovanov Rozansky, I don't know what an example is where this really can distinguish things that were not previously distinguished. Somebody else know?
I guess if you just go back to your simplest example, I actually, yeah,
This one?
yes. Now, you have an electric and magnetic big ones. What is the physical meaning of these invariants? What am I actually measuring? So these were electric or magnetic cross tubes. I'm sorry, are you a mathematician? Is that physics?
I don't want to answer that question.
Oh, okay, all right.
Whether I'm a mathematician, I mean.
So,
but
I was wondering if you have if I tell you that these are electric and magnetic fluxes, can